Hello, my name is Larissa Petroianu, and I'm presenting here RoOT, a light touch routing optimization tool for vaccine and medical supply distribution in Mozambique. RoOT was developed by numerous people from University of Washington and Village Reach with the support of the Ministry of Health from Mozambique. This presentation is going to be divided in introduction. We're going to talk about RoOT, the route optimization tool, discuss about the mathematical model behind it, and the indexing method that was used in the tool, give some numerical results, conclusion, and future work. If you want to know more about RoOT, it was published in the International Transactions in Operational Research, IFOR, and this paper is open for all. RoOT is a user-friendly routing scheduling tool for vaccine distribution in Mozambique. Vaccine distribution in rural and impoverished areas has many challenges, what makes it hard, such as unreliable vehicles, limited cold storage, road and weather conditions, road availability. And because of that, only minimizing transit time is not enough. We also need to minimize the use of unreliable vehicles and roads with poor conditions, so we can guarantee that the product is going to arrive to the people in need. As I said before, RoOT was developed by the University of Washington Village Reach with the support of the Ministry of Health for Mozambique. We have several discussions. A trip to Mozambique to talk to the final users to understand what they wanted, what was the problem, how the route was done on the daily basis, what was important, what were the main challenges they had. We had a prototype discussion with a lot of feedback sessions, a lot of improvements, and until we reach this final version that we're presenting today. This picture on the right is one of the training sessions of this final version in Mozambique with the final users. Those are the people that are going to use RoOT. However, due to COVID, RoOT was not fully deployed yet, and we're looking forward to it. RoOT has a simple interface, Excel-based with pull-down menus. The idea of doing it as an Excel tool was because the users, they are comfortable with Excel. That's a tool that they already know and they use a lot for other type of work, such as cost analysis. And we try to make RoOT and its sheets, input sheets, really close to what they already know in the daily basis with the other tools. And you use the pull-down menus to avoid problems like typos. RoOT also consider road and vehicle condition. And one of the things that the users asked us was to give a really good feasible solution fast. They cannot run RoOT for hours, so just in a few minutes. So because of that, use vehicle route and scheduling algorithm Versa that returns this good feasible solution in a timely manner. Some important factors of RoOT is that it has multiple objectives with different weights. It works with supply and demand issues, as we're going to see. It allows multiple routes per vehicle. Cost is not one of the objectives of the model. But the users ask us to have this visibility. So we add the cost visibility to the tool, and we're also going to show that later. And as said before, usability is one of the main things about this tool. We want it to be implemented and used, so it has to be easy. And so RoOT has one input file with 7 sheets, parameters, products, center capacities, demand, vehicle, distance date, and road condition. Also has one output file of 2 sheets, routes and products. And we're going to present that now. So for the input file, the first sheet, the parameters, it gives here, as you can see, for all the sheets, first we have the instructions in blue, and then in the parameters file, it defines which center distribution it starts, what time it starts, what time it ends, time spent each facility, the weight for the transit time, and the weight for the penalties. Here we call it risk because it's easier for them to identify, and it's like the penalty for the roads condition and the vehicle condition. The second sheet, we have the products that are going to be distributed. We define if it requires cold storage or not, and if it requires cold storage, the user enters information here with the quantity of dose per vial and the vaccine volume per dose. If it doesn't require cold storage, this area here is not going to be gray, it's going to be white, so it can add the quantity, the demand, sorry, not the demand, the volume per unit of this dry product. Then for each, the user enters information of each center, and if it's a national or regional health center, and the capacity of it, the cold capacity and the dry capacity. The fourth sheet, the user adds the demand for each product, and for each center, each product. Here you can see that if the user asks for more products than the capacity of the center, the capacity is reading for the previous sheet, we're going to have this red highlight. So RoOT does not consider the center capacity. It's going to distribute everything that the user asks here. But we want to give this visibility to the user so he can fix and distribute only the quantity of products that that center can store. The fifth sheet has information of each vehicle, if it's available or not available, the speed, the cost, the capacity, cold and dry capacity of the vehicle. And here you have the vehicle conditions, if it's always reliable, sometimes unreliable. And these vehicle conditions are going to be translated to numbers that are going to be used to calculate the penalties. And then the same idea we have for the roads. So here you have the road between two centers, and the user defines here if the road is fully paved, is that dirt road, is not accessible, and roads that are not accessible are not going to be considered by road. So the user can define that here in those pull-down menus. And again, these categories are going to be translated to numbers for calculating the penalties. All these categories will define with the users. And in the end, we're going to, the user has to add the distance between the centers. After saving that file, the user is going to choose it here from this pop-up window. It's going to choose that file that it was saved and click here to run route optimization. The default time now is 2 minutes, but it can be modified if needed. And after the 2 minutes, we're going to have this window giving where the results are saved. And they are going to be saved in the same folder as the input file. The output file has 2 sheets. The first one has the summary of all the routes and products distributed. Here the total distance, and as I said before, the user wanted to have the visibility of the cost. So we add here, we calculated and add all the costs here for per year, cost per fuel, and then we had cost per dose as well. And for each route, we have which vehicle was using that route, the condition of the vehicle, the distance, the cost again, but the cost for this route, the quantity of those delivered, and also have the capacity utilized by the vehicle, and then which centers it visited, and the time it left each center, and the road condition. The second sheet, it has the route. For each route, we have again the vehicle was used in this route, where it started, and for each center visiting that route, we have the capacity utilized from that center for cold and dry products, and the quantity of each product distributed. We have a user guide in the package, and the user guide explains how to install RoOT, how to use it, but it also gives and it also gives some frequently asked questions. What do we use for these frequently asked questions? We use them to explain in an easy way how to use RoOT, how to change the input files. Those are questions that they have in the daily basis. We define together. Like if what happens if the center changes location, if a new vaccine is added, a new facility, or if the code capacity changes, or a road is unavailable. So in the user guide, we answer each of those questions, showing how to change the input file to answer them, how to work with RoOT. And with that, it's easier for the user to understand it. A little about the model. RoOT is based on a vehicle routing scheduling with model with time windows and capacity constraints, and has two objectives: minimize transit time and minimize penalties due to the type of vehicle and routes. And the constraints for this model are the regular constraints for vehicle routing and scheduling problems, and they are supply imbalance constraints, capacity constraints, time and route constraints, and the use of available vehicles. However, we know that vehicle routing problem is an NP hard problem, and cannot always guarantee that we're going to be solved fast. It can take hours, even days, to find an optimal solution, and or feasible solution sometimes. So we decided to use Versa. That's a desindexing algorithm. Versa was presented to to do a to work with pickup of medical specimens, and we adapt that for the vaccine distribution. So Versa embeds this index rule that prioritizes the pickups in their case in here in the deliveries, so which node to visit and which vehicle to use. And it embeds this indexing rule in a branch-bound framework and dynamically constructs a branch to be traversed. So it creates incumbent solutions and it traverses the trees, pruning of and calculating bounds. So in the indexing algorithm, we have two indices that we use in Versa in RoOT. The first one defines which vehicle is going to be used for the route, and it's based on the vehicle penalty and the capacity code and dry capacity available of that vehicle. Both of the indices that we use, we are based on the constraints and the objective functions of the model. To define which node is going to be visited next, we use the penalty for the transit time, the wait for the transit time, and the penalties for and the, no, sorry, and the wait for the transit time and the transit time between the current node and the following one. And you have the wait for the penalties for that road, and the penalty for the vehicle being used. And the choice of vehicles and routes, they must respect the vehicle capacity, time limit, and road availability. Some of the numerical results that we have here, we have the three data sets that were given. They are real data sets given by Village Reach for three different districts. The vaccine distribution there happens for each district. You have a district store where the vaccine leaves and a vehicle goes and distributed for different health centers. And you can have one vehicle to do that, and then you can have to do different trips, or you can have two, and so on. We compare RoOT with three solvers: Groby, CBC, and GLPK. We use CBC and GLPK because we want RoOT to be free. We want RoOT to be available to all, and those are free solvers that could guarantee that. Gurobi is used here as a benchmark. We cannot use Gurobi as a tool in this route, in this problem because Groby has a fee, is paid, and you cannot guarantee that the government is going to have this, or the NGO, or who is going to use it, is going to have uh, resources for this for this license, and you want it to be available for all. But Groby is a really good solver, and use it as benchmarking. RoOT is always in red in these plots, and you can see here in this first one, Groby has the better solution in the beginning, but RoOT found a solution closer to it. Groby in this one found the optimal solution, and Verse was really close to it. In this case, GLPK found a solution that wasn't feasible, so it was in theory better than Groby, but when you saw the results, they were feasible. There was a problem in their algorithm. In these other two data centers, in data sets for two other province districts, we see that RoOT found a really good solution in the beginning, similar to Groby or even better than it. And in the end, in 1,000 seconds, it got solutions equivalent to the solvers. We also wanted to identify RoOT scalability. And for that, we create two data sets with 50 centers each. The simple one has no change in penalties for centers and vehicles. They're all the same. And the modified one has different penalties for vehicles and roads. So you can see with the simple, 50% simple, RoOT found a really good solution fast, really close to the one that is still that Groby reached in 1,000 seconds. And fast, and we found a really good solution before Groby found the solution. And here you can see that again in the modified that with different penalties, that was a harder problem. RoOT found a better solution fast, and in 1,000 seconds, Groby hadn't reached that solution yet. We also tested CBC and GLPK with these data sets, but in 1,000 seconds, they hadn't found a solution yet, a feasible solution. So as conclusion, the interaction between the teams, member the village reach and Mozambique government were essential to reach the objective to develop this tool the way that they wanted. And we are happy with. RoOT gives a good solution in a timely manner, as you can see, you saw in this previous plots. The user guide helps to answer these questions that they have in the daily work and help them to make simple modifications, input data. And RoOT is available in GitHub in English and Portuguese as open source for all users, especially NGOs, government, academia, and you want people to use and you want people to improve it. It's open to all. As future work, we want to have multiple day routes with mixed transportation modes because some health centers are in islands and we have to consider a vehicle, a car and a boat. And RoOT now, this version of RoOT doesn't consider that. We want a tool that populated this matrix because we know talking to the user and seeing the input files, that's the hardest part hardest information to enter is the distance matrix. So we want to develop a tool that can populate that matrix. And we continue working on improving the indexing algorithm to give it even faster solutions and better solutions. So we keep working indexing algorithm. And here's my email. If you have any question, feel free to reach out. And I thank you all for listening to this talk and all our supporters.